ability to use third-party apps, sir?
No. Okay, we'll go ahead right now. With this one class will start. I think yesterday I stopped somewhere here. Spring element, correct? The basic fundamental building blocks of mechanical system. We have started with the spring element. Three different type of elements. I told that spring element we started. Then other mass element damper. We talked about spring element yesterday.
My understanding is we have covered till the previous slide, sir.
This one? This slide? What you are seeing?
Yes, sir. Yes, correct.
Okay. So fine. Okay. Let us go quickly. We know that there are three types of elements in any mechanical system. If you finally dismantle the system, engine, machine, whatever it may be, finally get individual components or parts. Those parts can be defined as spring element, mass element, damping element, other name it elastic element, inertia element, or frictional element. The spring element can store potential energy. The mass element can store the dynamic energy, also called kinetic energy. And the third one is called damping element. Friction, it cannot store energy, it can dissipate energy. So these are the three elements which makes any mechanical system. Okay. Then already told you passive elements. Passive element doesn't create any energy or force or torque. And if we make a system using passive, so these three elements are called passive elements because they don't produce energy. One thing is they can store energy, potential this one, or dissipate, but they cannot produce. So these three elements are called as passive elements in mechanical system. If you construct a system, a machine, or this one, gearbox, engine, whatever, a subsystem or big machine, that is called as, the system called passive system. Because you are making all the components using passive system, using passive components. Instead of that, if you develop a system or a subsystem which produces energy, that is called as active system or active elements. Correct? For an engine is active element, electrical motor is active element, pneumatic motor is because if you give electrical energy, it produces mechanical torque, energy is produced. So those kind of systems are called as active systems. Then, as I told yesterday, there are two types of motion only in the universe. One is called translational, which is also called straight line, or also called linear motion. Other one is rotational motion, also called as circular or angular motion. Only two type of motion is produced in the universe wherever you go, rotational motion or linear motion. Okay, this is basics of mechanical system. Yesterday, I just started about spring element. A spring element is a translation mechanical element which can store potential energy. Okay, how will you make a spring? Take a wire which is made of spring material. We can spring steel, bronze, something like that. Correct? Spring steel or bronze, or these are the material using which you draw a wire. Correct? Solid wire. Correct? Then take the wire and make it as coil having a diameter. This wire is converted into a spring coil. So the coil has a diameter, I say the D, and it has an area, cross-sectional area became cylindrical in shape if you connect this one, and also it has a length, I say L1. So this is a spring. Okay, this ideal spring, if I apply, for example, take this spring, it has two ends, A and B. One end is B end is connected or fixed to a wall or something so that it cannot move. And the other side, you are applying a force. And through end A, you are applying a force. Okay, you are applying a force. The force can be compressive or tensile. It can be compressive or tensile force. If I apply compressive force, what will happen? Initially, when you try to, when the input, this is called input force. Input force is 0, spring has a length L1. Okay. Or for example, I say X1 because I have used the equation X1 and I say that initial length of the X1, not L1, original. The X1 equal to, for example, 10 centimeter length of the spring. Original wire may be 20 centimeter, 20 centimeter, 25 centimeter or 30 centimeter, you made as a coil. So it has a diameter and area. It has a spring length is L1. Now, when no force is applied, initial length of x1 equal to 10 centimeter. I am applying a force F equal to, say, for example, 5 Newton force. If I apply, what will happen? The spring will get compressed. Right? Because compressed, then the length reduces. The spring length reduces. Spring now will become something like this. Maybe coils become closer and length has reduced. This length is called x2 new length after applying 5 Newton force. Okay. Then I will say that there's a change in length of the spring. When there's no force, when the force is applied, I say delta x, change in length delta x equal to x1 minus x2. x2 is the new length after applying force. x1 is the before applying force. That is the original length. So if you do that, then I can relate an equation. That's what is shown here. The spring force. See, when I apply input force, spring opposes the force. The spring is giving opposite force in this direction, opposes. Correct? But I am giving input force. If input force is more than the opposition force, the spring is getting compressed. The force, this is called a spring's force. Spring's force is proportional to K into, in fact, this should be delta x, sorry, it should be delta x, which can be written as K into x1 minus x2, original length minus the new length after applying force multiplied by K, where K is called spring stiffness. Right? Sometimes they put subscript S to know that it is K subscript S, it is a spring stiffness. That is what they use, commonly used. Now, so this equation, what we call f of s equal to ks into delta x, which is nothing but ks into x1 minus x2, is called as mathematical model of the spring element. Mathematical model of spring element. What it means is I am connecting input output. Correct? I apply input force. Correct? When I apply, this is input. If I apply input force, there is a change in length. The delta x is change in length, which is nothing but x1 minus x2 is this, which is in the bracket, is nothing but delta x. Change in the length is the output. Now, in my mechanical thing, a simple component, a spring can be considered as a system or a machine. Multiple component by connected, that can be considered as machine. How you define depends upon what you are looking. So, spring, if you consider as a mechanical system, the Ks is called as system parameter. Note down. This is the word used called system parameter. Ks, which is nothing but spring stiffness, is the system parameter. Delta x is nothing but x1 minus x2. The original length, the new length after applying the force, is called as output. And f of s, which is the force you are applying, is going to be input force. So now this is called as mathematical equivalence of a spring. Okay, mathematical model. Once you have this mathematical model, without making the spring, I can find out what will happen. See, in this equation, I told you f s of t is nothing but ks multiplied by delta x. Delta x is the output, f of s is the input, and this is called system parameter. Ks, correct? Now, if I, for a given value of spring stiffness, for example, spring stiffness value equal to 10, correct? You take a spring, they say stiffness is 10 units. Okay, that is multiplied by output is nothing but my input. Okay, now if I vary my input 0 to 10 Newton, correct? No force, I am start increasing the force applied to spring, then the output changes. Change in length will start from initially there's a length, the length changes. The length changes 0 to 5 centimeter, correct? The change in length I am talking. Original length was 10 centimeter. As you apply, you become 9 centimeter, 8 centimeter, 7 centimeter, 6 centimeter, 5 centimeter stops. When I apply 10 Newton force, I say that the output is vary from 0 to 5. So from this, what we understand is the output is depends on two parameters. One is the system parameter, spring stiffness, or the input force. For a given input force, correct? If I vary the Ks, that means Ks, how I can vary? I take two different spring. One has a spring stiffness of 10, other one has a 5. Correct? The stiffness is 5. What will happen if you apply this one in this equation? Automatically you can find out what is the delta x output equal to, correct? Input Fs divided by Ks. Correct? This is what my the relation. The same equation can be written like this. Now here input equal to stiffness into output, or I can write output equal to the system parameters divided by Ks. Input divided by Ks, spring stiffness. Now we can say that 1 by Ks is called as system gain. 1 by Ks, correct? So I can write this delta x equal to 1 divided by Ks multiplied by f of s. You can write like both, it is that doesn't going to change, correct? So this part is called as system gain or transfer function. Note down. Whenever you talk about system, you will say transfer function, control system. If you talk that start about it, transfer function of the system or individual components. So that is fundamental. So from the mathematical model, what is my mathematical model? F of s equal to Ks into delta x. This is my mathematical model. From this, I can find out a transfer function, which is nothing but output divided by input. Correct? Output divided by input is called transfer function. So in that case, I know that if I write this f of st, then I'll get 1 by Ks. So 1 by Ks is called the transfer function of system, also gain of the system. Note down. Okay. So this is how we start developing mathematical model of any system. Our whole
Sir?
idea. Yes, please.
Sorry for interrupting.
Definitely. Please.
Sir, one question, sir. This gain constant or system parameter, whatever we spoke of, so typically, how would we arrive at its value, sir?
See, for example, spring stiffness, correct? Spring stiffness is the system parameter. Ks is the spring stiffness. No, that depends upon, correct, your shear modulus of the material. See, you are taking, for example, a wire, correct? Stainless steel, sorry, yes, wire, spring steel wire, correct? Or bronze wire. Bronze wire we're taking. Wire has some length, correct? And also it is a solid wire. Generally, it is a cylindrical shape. It has a cross-sectional area, correct? The cross-sectional area and the cross-sectional area, comma, the shear modulus of the material what you are using. These things going to decide what will be stiffness of spring. For example, I take a spring whose cross-sectional area is 1 mm square. Instead of that, if I take 2 mm square, definitely you know that thicker wire will have more stiffness. The stiffness of the spring depends upon the diameter of the wire which you are going to make as a coil. Correct? Apart from that, the shear modulus. Suppose instead of bronze, you take spring steel. Spring steel has more shear modulus compared to bronze wire. For same thickness of wire, bronze wire will have more stiffness, Ks, compared to this one. There's another formula is there, correct? Which relates the diameter of the wire and the area of the coil. If I take a coil, this area, cross-sectional area, the wire thickness, and all these things related, there is an equation. That equation you can use it. I think if I remember correctly, the Ks equal to G into D square, D4, D power 4, D power 4 divided by 8 into N into D cube. Okay, D cube. What are this? The small d is the diameter of the wire. This diameter, correct? I told you it is a solid cylindrical wire. It has a diameter. That wire diameter is called the small d. The capital D is this diameter. Spring, correct? Spring, you made a coil diameter. This is capital D, and this diameter is called a small d, and G is called a shear modulus. shear modulus of the material. That means if you use a spring steel, it has some value. If you use a bronze, that is value. If you use some other material, that varies. And of course, yeah, it is this one. This is number of turns, correct? Number of spring turns. This is 1 turn, 2 turn, for example, 3 turn, correct? Number of turns of the coil. So this is for note down this formula, correct? So this, so but generally, if you somebody may give this stiffness of the, if you buy a spring stiffness, you can calculate if you know all these parameters. If you know what material is the spring is made, and what is the diameter of the wire, what is the diameter of the spring coil diameter, number of turns, then you can compute. Otherwise, the value will be given. Okay.
It should be d cube, sir. Small d cube.
Small d cube, huh?
Yeah.
Yeah, I think d cube, but denominator, I don't. No. Denominator capital D cube, but where d power 4, if I am correct, I don't remember. You see the exact formula. Okay.
Okay.
So generally, if Ks is given, you can compute there's a formula like this. From that you can. I don't remember whether d power 4 small power 4 divided by capital D power 3. That's what I remember exactly.
No. You're right, sir. You're right. D to the power 4g at d cube by n. You're right.
Yeah,
Sorry.
this is equation, correct equation. Okay,
Yeah,
fine.
yeah.
So what if you don't know this one? But for this, you have to know all these things. What material, what is shear modulus, correct? Number of turns you can count, correct? You can measure the diameter. Thickness of wire, you can vernier, you can measure thickness of wire. But if you know the material, you can find out shear modulus. From that, you can calculate spring stiffness. Okay, that's how it works out. Okay, fine.
Thank you.
So yeah, now
Sir, I have a question. I'm sorry.
Definitely, please.
Sir, the question is that you have told that output divided by input is
Called
can be
as
considered as gain or transfer function.
Yes.
But what we have read is basically, or maybe what probably I'm wrong or right, I don't know. That transfer function is basically Laplace transformation of output and input at zero initial condition. So is there any something I'm missing out, sir?
No, you are 10% correct.
thing.
No, you are
Yes,
correct. Sir. You are correct. I have a system. For example, you have a motor. Electric motor you have, correct? It has only 2 wires. And you know that the motor on the top of the motor, the specification says that V can be given 100 volts. I can be, say, given 10 amps. P, power equal to, correct? Say 1000 watts. Nothing more than is there. You wanted to find out what is torque is coming. What is that you are interested? Motor is to produce a torque, and this is a mechanical torque and some angular velocity. This is output. What is input? You have to give a voltage. Correct? If you give a voltage, there will be a current flow. And so P equal to V into I. Correct? This is called electrical power. You give electrical energy, output is a mechanical power. Correct? I say that PM, mechanical power equal to omega into T. Okay? And this is called electrical. P should be equal to PM. Correct? Unless there are some losses, bearing a friction, all this thing. As long as theoretically we can say it should be both should be equal. Correct? Input power equal to output power. Now you have the motor, you don't know. You don't know how much current is taking, how much voltage you don't know. You have some X voltage you applied, some output is so much torque is coming. Correct? So you have a device which can measure that. So what is now we can find out the transfer function gain. Gain is nothing but input, output divided by input. Correct? Output divided by input. What is your input voltage? You are applying voltage. So for example, applied 10 volts. Because of that, there are 20 Newton torque is coming. For example, I said 20 Newton torque is coming. So what is the gain of the system? Output 20 is the output. Input voltage is 10. 20 divided by 10 is the gain of the system. Okay. You can get a number. But if you wanted to represent the transfer function in terms of this one system parameters, that's what we are discussing. Whole idea of the whole talk is about that only. When I say a system, my system is a spring. What is system? Spring as is a property. Spring property is simple, only is stiffness Ks. Correct? So I have a spring which has stiffness equal to 10. The system parameter, the spring is nothing but Ks. Now I am giving an input force. One end I fix, other end I am applying a force, that is input. Because of that, the output is nothing but I told you change in the length. Okay, I can apply input force 0 to 10 Newton. Correct? 1, 2, like this, I'll apply. Then I measure the change in the length. Originally, when the force was, this x-axis is force, F of t, y-axis is nothing but x of t, length of this one spring. Originally, it was here, 10 centimeter. This is 10 centimeter. This is 8 centimeter, 6, 4, 2, 0. Okay? When input was 0, force was 0, the length was this. When I applied work, for example, 2 Newton meter, 4, 6, 8, 10. Okay. When I apply 2, the length reduces to 8. That means delta x equal to 2 centimeter. Okay. Now I increase force to 4 Newton meter. The length becomes 6 centimeter. Like that, I can plot. Now, if I connect all this thing, I get the equation, straight line. This equation, if I write the equation for this one, because y equal to mx plus c, that's what you know. It is going to minus mx because it's falling, correct? Plus c. So this is called as straight line equation. This is nothing but mathematical model of your spring. Correct? That depends upon the spring stiffness. So the system parameter here is spring stiffness. Later, I will show that some more example. Little more complex system within another 5 to 10 slides. That time you will understand what the system parameter, what is the transfer function, what is gain means. Correct? So here, why we are calling it gain? See, for example, I am buying some item from somebody for 10 rupees. I am selling to somebody for 20 rupees. What is the gain? Whatever the value I sold in, correct? 20 rupees I sold. What is input? 10 rupees. 20 divided by 10 is my gain. Correct? That is represented, that is nothing but the transfer function. Gain is nothing but transfer function that depends upon the system parameter. In this case, the gain equal to 1 by Ks. Correct? The gain is nothing but 1 by Ks because you see here f of s of t equal to Ks multiplied by x of t. Correct? X of t is output, f of s t is input. So Ks is spring stiffness. So now I wanted to find out the transfer function gain. Gain is nothing but transfer function. Transfer function equal to output divided by input. Correct? In this equation, output is x of s. Correct? So that means I put x of s here. Right? This f of s will go here. Right? What will happen to the denominator? This will become 1 by Ks. Correct? So output of this one is going to be 1 by Ks equal to 1 by Ks. So gain of this spring, if you consider a system, is nothing but 1 by Ks, where the Ks is called system parameter. If I want more output, what I have to do? The output equal. Reduce the K. If you reduce the K, the gain increases.
Yes.
Okay. So that means for less amount of force, the spring will be compressed more. The X will be more. So that's what we say gain. I buy it for 2 rupees, sell it for 20 rupees. My gain equal to 18 rupees. Correct? So like that, here also, if I apply less force, if I get more output, I say my system has more gain. Here, the gain of the system is called transfer function. Any system, whether electrical, mechanical, whatever, the gain is called as transfer function. Gain is controlled by system parameter. Here I have only one element. Which element? Spring element. Spring element system parameter is stiffness. If I vary the stiffness, my change in length will vary. Spring output layer will vary for given same input. I keep the force equal constant, but if I vary stiffness, the output will vary. Or for a given stiffness Ks, if I vary the input, output will increase. Both I can change the input, get to more output, or for a given input, by varying the gain, I can get more output. Right? That's called system parameter.
Thank you, sir. Okay.
So now spring can be, you apply linear force. Instead of that, you know that if you take a spring like this, correct? One end is, this is called B end. A end I'm keeping open. B is connected, bonded or fixed. You cannot do it. I apply a twisting force. I twist this spring using a torque. What will happen? You will say that even if you twist the one end, keeping other together, the coil length will reduce. Correct? as I twist clockwise, it will reduce. If I twist angular, length will increase. It is as if applying linear force. So that's what this is second equation. I can write the spring mathematical model if they applied for a torque, that is rotational force at one end of the spring, other end is fixed, then I can write this equation. This equation nothing but torque is the input. Instead of force, I'm applying a torque, that is input. Change in angle, output is nothing but this should be delta theta. Sorry, small mistake. Kf into delta theta, where delta theta is nothing but delta z minus delta w. Correct? This is the when initially this spring was at see, we know that the 360 rotation means this is 0 degree. I apply a torque, say for example 5 Newton. It twisted by say 60 degree. Correct? This end has come to this one. So automatically coil will get compressed. Correct? Then it will get compressed. But the end will come here. Instead of here, it has moved to new angle. If you measure the angle, that is what I call it theta z. Correct? So initial angle was 0. Now by giving a torque of say for 5 Newton, the end A end is twisted by so many 30 degree. So 30 minus 0 is the delta theta multiplied by spring stiffness is the torque. So again, I can get a equation. So this how the spring element can be represented. So please note that the whole idea of this one is how to write the mathematical model, because later we are going to simulate, and without making the physical component, using the mathematical model, we can get what you call virtual simulation. Computer write the program and find out and vary the stiffness and find out per given input how much delta x happens. I keep the stiffness constant. I vary the force in C program. I say f of s equal to, correct, t equal to vary from 0 to 100 or 0 to 10 Newton. Correct. I say that k equal to 10. Find out x of t. I can write a C program. So if I vary my input, how much delta x is varying? The system computes and provides. I can plot a graph. So this is nothing but designing the spring. Designing spring is nothing but how much displacement the spring should. For example, shock absorber. When the force is applied, how much it should get compressed. Correct? How much the sprung mass should move up and down. That can be calculated in computer without making the physical spring. That was the whole idea. Correct? Without making physical spring, I can write a program by varying input output. I can always find out output my output for a given input, for a given stiffness. What will be the output? I can always find out. That's what mathematical modeling. So from this, what we understand is we can see that force or torque developed by the spring is directly proportional to the difference in the displacement, angular displacement or linear displacement of the one end of spring related to the other end. Other end is I fix. I told you I can fix the one end and applying a force F of t, or I can fix this one end and other end I am giving a twisting for torque. So theta varies. Here the x varies, length varies. Here the angle of the other end. So automatically, coil also get compressed. So this is how we find out mathematics. This is called mathematical model of single element of mechanical system. Now, when I talk about spring element called as ideal spring element and practical. Ideal spring element can store potential energy when you apply a force. Correct? Spring is getting compressed. Then, if you keep the force of this one, the energy is stored inside the coil compressed spring. If I remove the force, spring comes back to original shape. That time it releases energy. Correct? While storing energy, stores a potential energy. And theoretical spring should not have any mass. Correct? I said it is a spring element. That means it is spring, it can store energy, but it should not have mass. And it does not dissipate energy. Both it should not do. If it dissipates energy, it is called a damper. Correct? And if it has a mass, it is called a mass element. It is not a spring element. So theoretical spring will be this, and it will have a linear behavior. If I vary my input force 0 to 10 Newton, correct, spring force, the delta x will vary from 0 to 10 centimeter, for example. So it should have linear, correct. If I vary 5 means the delta x will be 5 centimeter. If it is 6 means it will be 6 centimeter change in length. So if it is this kind of character generally expected, this is theoretical point, but practical spring cannot. Can you make a spring with do you have any element in a periodic table which has zero mass? Even gas, hydrogen, that also has individual atom has some weight, right? So you make this bronze, you make a stainless steel, spring steel, whatever may be, having some thickness, having some volume, having some length, definitely it has a mass. So it is not, this condition not possible practical. That's why that the practical spring has some inertia because it has mass. And it also may have some friction or damping if the coil is moving inside a liquid or moving inside a gas. Because we make a spring, the spring is it is in the atmosphere. When you compress the spring, the air is touching. Air density is very low. Still there is a small amount of friction. Some energy is lost due to friction between the spring coil and the air surrounding it. If it is inside the oil friction, touching, oil surface is touching, there is a contact, there is relative motion between oil and the spring. So some energy practically not possible have, this is also not possible. Again, spring, practical spring have a linear displacement, correct? When I change the force 0 to 10 Newton, our delta X will vary from 0 to 10, only for only certain linear angle, region. Beyond that, it won't. Then I told you that spring can store energy. How much energy spring stores, which is called as E, is nothing but C divided by F square by 2, which can be written as K divided by Kx square divided by 2. Where is K is spring stiffness? This is the displacement, correct? Delta X. I can write X or delta X, you can say delta X square multiplied Ks divided by 2 is the amount of the energy stored in the spring as a potential energy. So this is what I told, correct? So this is the change in length, delta X, correct? If you apply tensile force, the spring length will increase, correct? As I apply tensile force, I'm pulling, correct? If I pull from original length, increase the delta X become positive. Similarly, if I apply compressive force, from original length reduces. You can see that only for small region, the linear relationship is maintained. Correct? Beyond that, it becomes non-linear. This is the problem in the practical spring. So, if I want to have a linear relation, you should operate only in this region. Okay. Next element is what we call a damping element. Correct? Or damping element also called as spring element. Or frictional element. They called as frictional element. The damping element is this in which friction is existing in between two physical components whenever there's a relative motion. Correct? If there are two objects, correct, this is the object 1, this is object 2, and with if this is moving in this direction and if this is moving in other direction, they are touching with each other. Please note that they should move with respect to each other, relative motion, opposite direction, and also should have contact between two. Then here frictional force is created. Already we know that, right? That frictional force is also called as damping force. Frictional force also called as damping force. So the typical damper can be made. Sometimes we know that most of the time you don't want friction. Whenever you want motion, you want frictional force to be the damping force to be 0. If there's a friction, you put lubricant to reduce the damping. But sometimes in mechanical system, we want voluntarily produce a opposing force or damping force to stop the motion between two components. In that case, you will use damper or frictional system, which has two moving parts sliding over each other. Okay. Then instead of that, there are different type of dampers, metal to metal contact, or a piston moving inside. Yeah, a completely enclosed cylinder. This is the cylinder, glass cylinder. Please see the both ends are completely enclosed, and you have the piston, and piston is connected to a stem. The stem is connected to a moving element. Correct? I want to arrest the movement of this one. Then, because I have fixed or connected, correct? Now, if this item moves, what happened? The body is fixed, correct? The cylinder is fixed, it cannot move. The piston is connected to moving object or element, and this movement should be, the moving object movement should be arrested. In that case, but what will happen? I fill this cylinder with some oil. Inside this, there are chamber A, chamber B. There are two chambers with respect to the piston. In both the chamber, I fill with fluid or gas. I can fill with fluid, which can be a liquid or a gas. It can be a liquid or a gas. I can fill it. Both chambers completely filled. There's nothing. Correct? Now, if I try to move, if it is filled with gas, the gas can be compressed a little bit. But if it is filled with liquid is incompressible. Correct? It is an incompressible fluid. Then the piston cannot move. Generally, what will they do is, in a typical damper, which we see shock absorber, you will see a damper in which I have a piston, cylinder completely enclosed. Inside it, there is a piston. Okay, piston shaft is coming out. This is connected to moving object. Correct, and this is my piston. Okay, and in the piston there are small holes, which is called a orifice. Maybe 1 or 2 or 3 result. And this orifice has some diameter D, correct? Hole has a diameter D. So if I fill this one with some fluid, completely filled, if the piston is moving, what will happen? This is called chamber A, this is chamber B. If I move the piston from right to left, the fluid from A will go through this hole. Correct? It will flow like this from chamber A to chamber B as the piston is moving like this. Instead of that, if a piston is pulled this direction, correct, the fluid from here will move from this way direction through these holes. Correct? Rate at which the fluid is moving, or velocity, rate of fluid movement, or velocity of the fluid going to the small holes, which is called an orifice. Correct? Depends upon the viscosity of the fluid. Correct? Viscosity of the fluid and also the diameter of the orifice. Correct? So now, because the fluid cannot move freely, because it has to go through these holes only from chamber A to chamber B, it produces an opposing force of the movement. Correct? If piston is moving like this, the fluid will give a force opposite direction. That is called a damping force. I call it FD. FD is proportional to velocity of the piston. That means automatically fluid flowing through this one, fluid velocity going through the orifice, also the viscosity and velocity of the fluid filled in the damper decides what is the opposing force generated when the piston tries to move. So that means this force is acting opposite to the piston movement. So I can arrest the movement. For that only damper is used. So I told you damper absorbs energy. Why? Because I am moving this one, the piston connected to moving object. Moving object generates energy. That energy is absorbed by the this one damper. So the movement of the moving object is arrested. For this only we are using damper. Okay. When we talk about dampers, we talk about friction. They say it is a frictional element. Okay. There are 4 types of friction. One is called static friction, which is called stiction. The force required to move. For example, I have a table, correct, on which I have a block. For example, solid iron block measuring, for example, 10 kg something. Correct. I am applying a force F, and because I wanted to move this 10 kg mass towards right side. Correct. When this force is 0. X of t is the displacement. Displacement equal to 0. As I increase the force, 1 Newton, 2 Newton, 3 Newton, 4 Newton, it is not moving. Once it reaches a certain value, correct, you will see that suddenly the block start moving. Then X of t start increasing. Correct? So for certain force, the amount of force needed to move the block, which was static condition, to a dynamic condition, that is called as static friction. Correct? Correct? What is the static friction? Static friction is the friction between the object which is trying to move and with respect to a static object, which is nothing but a table. This friction, the force which opposes the forward motion is called as static friction. But once the blocks start moving, say for example, F of t equal to 5 Newton, correct? It start moving. Then what happens? The static friction becomes zero. Correct? The static friction becomes zero. Static frictional force I call F substitute becomes zero. But as long as it's not moving, there's a force. Correct? But once I give sufficient input force, then the input force is more than the opposing force, static friction, then x of t start increasing. So that means motion starts. Once motion starts, the static friction becomes zero. The next one is called kinetic friction or Coulomb friction. The force exists only when relative motion is there between two objects. The block is moving. Only when block start moving, this friction, kinetic friction, come to system. When block is not moving, the kinetic friction is zero. Okay, static friction alone is there. Okay. Now, the third friction is what you call a viscous friction. Viscous friction is a force between two moving surfaces separated by viscous fluid. That means I have a block. Okay, I have the table. Correct. This is my table. This is my block, and in between I fill it with some oil or liquid, some liquid. Correct. The red one is the liquid. The liquid can be water, oil, whatever, maybe some viscosity. So now if you apply a force, correct, there's a motion. During the time, there is a friction created by the liquid. The interaction of the liquid of the surface, which is nothing but table, and the top one is the mass, moving mass. So this force is called as viscous friction. It is generated when two objects are moving related to each other, and there's a viscous fluid in between. The force which opposes the motion between this is called as viscous friction. It is linearly proportional to velocity. Correct? It linearly proportional to the relative velocity we call. Because table is fixed, this is moving. So with respect to table, the object is moving to 10 meters per second. Correct? That is velocity. So I will say that relative velocity is 10 meters per second. Only when it is moving, the viscous friction is there. Similarly, only when the two objects are moving with touching each other, there is a kinetic friction. That is, see, kinetic friction we talked in terms of dry surfaces. There's no lubricant in between. In this case, there are two objects, solid objects moving with each other, but in between there's a liquid, correct, or a fluid. It can be air, it can be a liquid. In that case, so we can write, if it is a damping element, we can write the transfer function. First, we write the mathematical model. Mathematical model, this is I call a damping force FD. FD equal to KD into d by dt of x, where x is nothing but displacement. Correct? That means d by dt x is called as velocity. So damping force FD equal to KD, where KD is called a damping constant of damper. Note down. Damping constant of damper is called KD. KD multiplied by velocity is called as damping force generated by the damper. This is for linear motion. Instead of that, you can have two objects moving rotational movement, but touching each other. Correct? A cylinder moving inside but touching each other. Then you apply a torque. Input is a torque. Again, it has a damping constant d by dt of theta. Correct? Angular displacement. This is nothing but omega. D by dt of theta is called as omega. Omega into kd, which is nothing but damping constant, damper, is equal to torque applied. Correct? Here force applied, or this is, I can say TD, damping torque. TD, kd is called damping constant. Okay. So this equation represents, both the equation represents the mathematical model of a damper. It is a mechanical.
Sir,
Yes, please.
X I can able to understand, but theta, how we are representing here?
No, it is a rotational movement. Correct. For example, I have a cylinder. Correct. I have another inner cylinder. Both are touching each other. The outer cylinder is fixed. The outer cylinder is not moving. Correct? They fixed. The inner cylinder is connected this one. I am applying a torque. I am applying a torque to the inner cylinder. Correct? So initially it was like this. Before rotation, the theta was 0 degree. Now I am giving a torque. So it's the angle increases. Theta increases 1 degree, 2 degree like this. Right? That's what we are talking. Right? The angular displacement d by dt means angular velocity, rate at which the inner cylinder is rotating with respect to outer cylinder. That depends upon the damping torque.
Got it, sir. Thank you.
Okay. Now, whenever damper, I told it dissipate energy, doesn't store energy. Spring store potential energy. Damper dissipate energy. How? It generates heat. Correct? If you know the rub your hand, friction is there. You will see that your hand is getting heated. Correct? The frictional force, the energy you are supplying to both hands is absorbed and created as a heat because of rubbing. Correct? So damper always dissipate the given energy as a heat. Correct? Then, sorry, the power equal to in the damper equal to force multiplied by velocity. Correct? Force by velocity equal to this. So we can write power equal to F into d by dt of x, which is nothing but this is velocity. Correct? So this is nothing but kd into d by dt of kd into d by dx is nothing but v square, velocity square. Power equal to kd into, this is what the power dissipated by damper can be computed like this. If you know the damping constant and if you know the velocity, linear angular velocity, you can compute how much power the damper is dissipating. Okay. Already I told you about the friction, different type of friction. Static friction. Correct? You can see that the static friction is there when there is velocity 0. Velocity 0 means nothing is moving. There are two objects, they are touching each other. One object you are trying to move, but you are applying force, but it's still not moving. Correct? As long as it's not moving, there is an opposition force. That means velocity 0, opposition force. Once the object starts moving, velocity increases. From 0, it becomes 1, 2, 3. Automatically, you can say that the static friction 0. Static friction there as long as you are trying to move, but object is not, there is no relative motion. That time, whatever the force, opposing force which stops the movement of the one object with relative, that is called a static friction. So it is 0. When velocity is 0 only, the static friction is there. Next one is kinetic friction. Kinetic friction is 0 when there is no relative motion. Correct? That means during static friction, kinetic friction is not there. But once the one object start moving related to other, motion velocity is there, immediately you will get the kinetic friction. Correct? Kinetic friction jumps to 10 Newton. You can see that. So it can be positive or negative, this one, negative, depending upon with what reference you are taking. So that means, but it is once you start moving, this amount is fixed for a given element, depending upon frictional constant and the force acting on the body. Correct? This is called as, Fn is called as normal force. Normal force acting between the two moving relative objects is called normal force. Multiplied by mu is called as frictional constant. Correct? So once they don't, you can find out, but it will be this one. The third one already is a viscous friction. Viscous friction also is 0 when velocity is 0. But when velocity is positive, the viscous friction is positive. And when velocity is negative, it is negative. But it is a linear. Correct? It is linear. But you can say this is constant. Correct? Once start moving, the kinetic friction becomes constant, but depends upon the damping constant mu, frictional constant mu and this one. Here, this directly proportional to velocity, you can say increasing. The last one is if your object moves in a fluid, we call drag force. Correct? Drag force is nonlinear. You can see that when velocity is 0, there is no drag, but it can be a positive drag or negative drag depending upon the direction of the motion, but the motion is the drag force created is non-linear. We know that it is v square, velocity square. So that's why it is non-linear. Okay. I think I'll stop here. Next class we'll talk about mass element and we'll talk about more about how to build mechanical systems, simple mechanical systems. and how to write mechanical equations, transfer functions for the
Yes, sir.
mechanical. Yeah.
Last one is the
Excuse me?
No, sir.
I'm not.
Nothing, sir.
Mechatronics.
Nothing, sir. Listen. No, no, sir. What else, sir?
Sir, I wanted to
not-
ask something, but I stopped thinking someone else wanted to say something.
Yeah, tell me, Amit.
Thank you, sir. So you were, sir, other day we were discussing about the example of, dynamic suspension, right, which will adjust according to road conditions, etc.
Yeah,
So this
active
is-
suspension.
Yes, active.
Using MR damper. Yes.
So there, based on what example we just read, my assumption is that the concept originates from by varying the spring constant or stiffness constant. Is that right to assume, sir? Or
No. Shock absorber contains two parts. One is a spring, other one is a damper.
Yes, right.
Correct. Spring cannot be changed. We said it called active damper.
Yes, right.
Damper constant is because I have worked on it. I work with a company.
Okay.
Correct. Still I have the fluid. MR fluid 1 liter costs 80,000 rupees. I just bought it 1 year before. One student want to work a project on it, active suspension with me. But that student left the institute. In first year MTech, regular MTech, the first year I attended my MTech mechatronic class. So I was talking about that you want to do the project. I imported oil, all this thing from UK, spending 80,000. After first year, he got a job, he left. So the fluid is with me. If somebody want to work on this as a project for your industry also, we can work on it.
Okay.
I have the fluid, already work on this for last 15, 20 years. I have test rig everything. Correct? That is going to change damping color damper. MR damper, it is called MR damper.
Okay, so, okay, sir. Understood. Thank you.
Okay. We'll see you on Monday. Thank you.
Thank you, sir. Thank you so much.
Thank you, sir.
Okay. Bye.
Thank you, sir.
Thank you, sir.
Thank you. Take care. Nice weekend.
Thank you, sir. Thank you, sir.
Thank you. Thank you, sir.
Okay. Give your attendance as chat, miss.
Yes, okay. Sure, sir.
Okay.